Thank you very much. Well, I really don't know where to start after that introduction. Nowhere, perhaps. I'll try to do my best to be a Johan Rockström impersonation for the rest of the day today. It's a real pleasure and an honor to be here to talk to you at this 75th anniversary celebration. We're going to cover a lot of territory in this talk, and I would like to do a little bit of advertisement for a new bunch. The first line, that big, long Swedish thing up there, is a partnership between a number of Swedish research funding agencies, the Swedish aid agency SIDA and the Royal Swedish Academy of Sciences, to really work in an interdisciplinary way to get Swedish scientists involved in international interdisciplinary work. What I'll be talking about, I couldn't fit the title that's in the program onto one slide, so I changed it a little bit, and this is what I'll talk about today. Where will we go in the next 20 minutes or so? I'd like to first talk about the Anthropocene, our new epoch, the epoch where we humans are actually the driving force, the major driving force on many elemental cycles of our planet. We'll talk about a few transformations towards sustainability, because this is really much a gathering of people looking for solutions, looking for how to make things work. And try to focus in on one example of transformations that we will have to put into place. That's how do we feed 9 billion people on this planet in a sustainable way. So let's start off in the Anthropocene. And I'll start off with this plot, which actually is an homage, if you will, to Danes. And it was wonderful to know that I'm among friends. Coming from Sweden, it's great to know you're among friends when you get to Denmark. But this particular plot starts here with time on this axis. This is age in thousands of years before the present. That's almost now. That's 100,000 years ago. And on this axis is a measurement of an oxygen isotope ratio, which is proportional to temperature. It gives you information about the temperature in the region where this was taken. This comes from Greenland, and the Danes are just famous for digging up ice in Greenland. So let's take a look at this, and we can see that temperature down is cold in this picture and up is warm. But we can see lots of variability, and generally it was colder 100,000 years ago than it was today. But the last 10,000 years here, roughly, have been relatively stable, compared at least with the previous 80,000 years during the last ice age. What I've also put on top of this picture are a few waypoints in our human history. So let's look at the last 100,000 years of our human history. Here, right about there, 85, 90,000 years ago, roughly, we, modern humans, left the African continent. Hadn't gotten outside of our backyard until then. That's when we left and started migrating around the world. Didn't get to Australia till about over 60,000 years ago. Didn't get to our neighborhood now until maybe about 40,000 years ago, 35 or 40. So we're pretty young, and in all of that time, all of the time that we were out wandering around the world and populating it and throwing rocks and sticks at antelopes and gathering nuts and berries as we went along, we were hunters and gatherers, and we were living in a rather unpredictable and much harsher condition than we have now. So here is when we started doing things like stopping throwing sticks at antelopes and getting them to stay nearby, having cattle and learning how to cultivate crops, building what the society that we know as a society at the moment. All of that happened in a very stable period of our environmental history, the Holocene, as it were. Well, we're no longer really in the Holocene. That's that period. We're no longer really in the Holocene. If we take an even longer look back in time, the first one was 100,000 years. This particular plot now, from a different ice core, and it wasn't, well, Danes were involved in this too, but it wasn't Danish territory this time around. This is from Antarctica, Dome Concordia. And this particular ice core, in which we're measuring carbon dioxide concentration in parts per million by volume, goes back 800,000 years in time. So now we're going from roughly about 150 years ago to 800,000 years back in time. And if we look at this, we can see that carbon dioxide during those 8 ice ages and interglacial periods, the last 800,000 years, has varied between rather defined limits. It's varied between about 160, 170 parts per million by volume to not more than 300 parts per million by volume. In all of that time, where are we today? 390 parts per million by volume. That's not a red line that I sort of just drew on this graph. That's actual data taken from the Mauna Loa volcano from 1958 to the present, plotted on the same time scale as the ice core data. And it shows a couple of things, really. First off, that at least for this important greenhouse gas, we are now way, way outside the natural range of variability for our planet for the last 800,000 years. And secondly, that we've gotten there much more quickly than anything that we can see in the past. So things are changing in a large way, and they're changing very rapidly. That was carbon, or at least one part of the carbon cycle story. Here's nitrogen. And if you look at the upper panel here, we can see nitrogen from 1890. The lower panel is 100 years later, nitrogen cycle in 1990. The pictures here show different reservoirs. So, well, that's not a picture, but that's nitrogen in the atmosphere in an inert state, N2. These are natural terrestrial ecosystems. That's that picture here. Here we have managed terrestrial ecosystems, farming and agriculture. That we've got fossil fuels burning. Here we've got forest fires and fires burning, biomass burning. Over here we got some fish in the marine domain. The size of the arrow going between those reservoirs is proportional to the amount of material, the amount of nitrogen moving from one reservoir to another. And you can see in 1890, the major transfer was from the atmosphere into natural terrestrial ecosystems, nitrogen fixation basically through natural biological processes. There's a big arrow here. That's one single industrial process, the Haber-Bosch process, that allows us to turn nitrogen in the air into something that we can put on our fields. And it doubled the amount of nitrogen that we put through the Earth system. And it changed that picture completely. Coming back to our historical ancestors, our modern humans wandering around, we're breathing from an atmosphere today that none of our modern human ancestors ever experienced. It's entirely new. Let's take a little closer look at the terrestrial systems. This is a wonderful publication by John Foley and a football team of collaborators very recently, where he's looking at the land use and what we use land to do. So the green colors here, the deep greens are that particular area of land is used almost entirely for crops. The deep orange colors are that bit of land here is used almost entirely for rangelands, for cattle, essentially. And if we look at the combination of cropland and rangeland, we're occupying about almost 40% of the land surface to either raise our crops or raise the cattle that we want to feed them. So we've got a global impact. We are in the Anthropocene. And if any of those pictures haven't convinced you yet, that one hopefully will. That's light seen from space. Okay? That's not some artist's conception of light seen from space. It's actual satellite imagery of lights seen from space. We're everywhere on the planet, and we actually do have a planetary impact. If you start looking at the planet at a planetary scale and do something that we're not all that good of, or at least we've gotten worse at it with time since Newton was around, basically, that's putting a big picture together. If you start looking at the planet on a planetary scale, you start seeing sensitive areas where if you give the planetary system a little bit of a push, it might exhibit a large change, a nonlinear change given a small forcing in science speak. There's a lot of these around, and the more you look, the more you see in many ways. I'm certainly not going to talk to all of these today, but I do want to stress, for instance, about 8,000 years ago, the Sahara, which is now a desert, was a savanna ecosystem. And it changed relatively rapidly from a savanna ecosystem into a desert one, more rapidly than the forcing. The change in solar radiation coming in from the sun would have driven it had it been a linear system. Anyway, the more that you look at the planet at the planetary scale and look for emergent properties, the more of these that you see. And so a number of years ago, the guy that should have been talking to you today, Johan Rockström, and a bunch of others of us got together and asked the question, well, we are in the Anthropocene. Can we identify and quantify different parts of this process that we can say we don't want to be beyond a certain point? If we go beyond a certain point, then we risk moving the Earth system, the entire thing, into a different state. one that might be different from that relatively stable 10,000-year Holocene period that our societies grew up in. So that was the original paper. And we called these things planetary boundaries, these boundaries that we didn't really want to exceed. And they've got a few characteristics. One is that they're functions of the way the Earth system works. So one is in fact a chemical equilibrium. I'll get to what they are in just a little bit. But one is a chemical equilibrium. It's simply the way the Earth system works. They're non-negotiable in the sense that you don't negotiate with a chemical equilibrium, regardless of how good a negotiator you really are. Secondly, each one has some sort of control variable over which we have influence. It could be the amount of nitrogen or phosphorus that we cycle through the Earth system. It could be the amount of carbon dioxide we put into the atmosphere. It could be the amount of land that we use for agricultural purposes. So there's some control variable that we can identify, quantify, and over which we humans have control. An interesting aspect of these planetary boundaries is that they all involve a normative choice. They all involve saying, okay, what risk level are we comfortable with? Do we want to risk losing the entire Greenland ice sheet irreversibly? Or what level of risk of that happening are we comfortable with? So that's the normative aspect of these planetary boundaries. They operate on timescales over which we have control. That ethics and political decision-making is influential. And so these things aren't on millennial timescales. Most of them aren't even on century timescales. They're on the timescales of decades, if you will, or perhaps a very small number of decades. Finally, that if we recognize where these boundaries are and we stay on the right side of the guardrail, then we can create what we called originally a safe operating space for us. It's not that you can party until you drop within these boundaries, but staying within them reduces the risk of moving the Earth system into a state that we perhaps wouldn't recognize. So very schematically, you've got a control variable on the bottom here. You've got some sort of response here. Oftentimes, that is a nonlinear response. It doesn't have to be a threshold necessarily, but in many cases it is. Then you have essentially a boundary, which we put at the lower end of that zone of uncertainty. We don't know where all of these transition points may be. Some are easier to identify than others. Ocean acidification, for instance, is a chemical equilibrium that is well defined. But then our safe operating space is on the right side, the correct side of that boundary. So when we started this analysis in probably about 2008, I guess, we didn't know if we would find any of these things, if we'd find 615, and we ended up with 9 that we could identify, and 7 of which we could quantify. We felt confident enough to put a number on. Whoops, before we get to those, climate is one, ocean acidification another, how much ozone we have in the stratosphere, the third, how much nitrogen and phosphorus we cycle through the Earth system, freshwater use, land use, biodiversity loss, and the 2 that we couldn't quantify have to do with particle loading in the atmosphere and chemical pollution. I don't want to talk in detail about all these, but I'd like to show how they might be used as a framework for strategic decision support. But before we get there, let's take a look at where we were in the past in terms of these planetary boundaries. So if we look at the pre-industrial period, that's that little dot right in the center of the diagram there. We were well within all of these planetary boundaries in the pre-industrial world. The 1950s, for the boundaries that we felt we had sufficient data to quantify for that period, we were also well within these planetary boundaries. If we look at the 1970s and 80s, already at that time we stepped across the nitrogen boundary. That's the Haber-Bosch process in the Green Revolution, which was actually a miracle for us. It was a miraculous process for us, but it comes at a cost. If we look at the 90s and the noughties, we're even farther across the nitrogen boundary. We've crossed the climate boundary at that point. If we look at the latest data, we can see that we've crossed the biological diversity boundary. We're even farther across nitrogen and climate, and we're closing in on some of the others. There's one success story here. That's the ozone boundary. And you can see that we're actually moving in the right direction in terms of the ozone boundary. The Montreal Protocol signed in the mid-1980s is actually working and it's moving us farther away or farther from that risky area that we would not like to be in. What does it mean to be across a boundary? I mentioned that we're across 3 of them, and I'd like to just spend a moment or two talking about one of them, the climate boundary. If we look back in time, and this goes even farther back in time than the ice cores, this is a sediment core, an ocean sediment core. And you can estimate carbon dioxide concentrations from the sediment core, and this goes 65 million years back in time now. So this is where the dinosaurs disappeared, roughly, at that point. Here, this is a logarithmic scale, so that's 1,000 parts per million by volume carbon dioxide concentration. Here we have 100, 200, 300, 400. So remember, we're at 390 at the moment. We're just below this green line now. So back here, about 50 million years ago, or thereabouts, we know that we didn't have any major ice sheets. There wasn't any major ice sheet in Antarctica. There was no ice in Greenland. The planet was essentially ice-free at this particular point. And that's when we had carbon dioxide concentrations of about, well, here's one point below 400, but usually about 500, 600, 700 parts per million by volume or larger. Okay? So in that condition, the planet was ice-free. Here we've got carbon dioxide concentrations where we do know, at least here, we had major ice sheets in Antarctica. The Greenland ice sheet didn't show up until right about then. Okay? So to have major ice sheets on the planet, the evidence that we have is you need carbon dioxide concentration somewhere in this level. By the end of the century, if we follow a business as usual scenario, we'll be at the red line by 2080. We're moving into risky territory. Okay? We can't say how fast a stable ice sheet like Greenland might go away, but what we can say is looking at this paleo data, that in that condition we know we didn't have major ice sheets. In this condition we know we do. Make up your own mind, essentially. So let's look at transformations. Given this framework, and if we're looking at the activities in a sector basis that most affect our environment, most push us into these areas that we don't want to be, there's 3 really. There's the energy sector, the transportation sector, and the agricultural sector. We need to transform these 3 sectors to come to a sustainable society. Let's look at one of them. Let's look at the agricultural sector, producing food for 9 billion people. How do we do that at the moment? So this cartoon illustrates how we produce food for the 7 billion of us that are on the planet at the moment. And actually, we do produce enough food to feed everybody on the planet at the moment. All of us can't afford it. And we're not getting that food to the people who need it most. It's not that we can't produce it, but the way we produce that food is here on the land. We use land, obviously, for crops and for cattle, as John Foley's wonderful picture showed a while ago. But we produce that through using nitrogen and phosphorus fertilizers. We do that also through irrigation water, either from groundwater sources or from rivers. It rains on our crops as well, but we do use a lot of irrigation water. Some of that nitrogen, the nitrogen that we use ends up as another greenhouse gas, N2O, but a lot of it runs off into coastal areas. And that brings us to the marine domain here. In terms of producing food from the marine domain, we can go out and fish it, that's this part of the cartoon, or we can farm fish. So let's take a little look. We'll start in the marine domain. We'll look at how we actually do this at the moment and what we can produce. So let's start looking at fish catch, wild fish catch. So there's a couple of really interesting plots here. This particular one from the UN Food and Agricultural Organization shows landed fish catch from the 1950s, that's 1950, to 2006, and this is in million tons, and you probably can't read the numbers back in the back, but that's 100 million tons here. And we can see that from the 50s until about 1980 or so, there was a general monotonic increase in the amount of fish that we were catching. But that has essentially plateaued out in the last 25 years or so. So we're not catching more fish at this point. This particular plot shows where we're catching that not more fish. So this has the same time scale, 1950 to a little past 2000. The red colors, that's 10 million tons of landed fish. That's 1 million ton of landed fish. It's a log scale too, unfortunately. But it shows that in the 1950s, we were fishing down to, well, mostly about 300 or 400 meters. Sometimes down to about 700 or 800 meters. But now we're fishing farther and farther, or deeper and deeper into the ocean to produce the same amount of fish. What I don't show here is we're going farther and farther offshore to get it as well. If we look at fisheries now, that was the landed catch. If we look at fisheries and the state of fisheries over that same time period, so this is 1974 to 2006. There are 3 different plots here. The squares are the fisheries that are fully exploited. They're at their maximum production potential. And it's been about half over that entire 30-year period, roughly. The triangles here show those fisheries that are overexploited, that have collapsed, or that are recovering from collapse. 1974, that was about 10%. 2006, that was about 30%. So at the moment, 80% of our fisheries are either at their maximum production levels or overexploited. So if we want to produce more food from the marine domain, there's not a lot of wiggle room in terms of going and catching more unless we change our fisheries policies. So let's talk about fish farming. We're not going to get to fish farming just yet. We'll want to take a detour back to the land for the moment and talk about how we produce food on land. Well, I mentioned that we use nitrogen, and this is the amount of nitrogen that we've been using since 1910 up to about the mid-1980s. This period here is what a good friend and colleague, Will Steffen from Australia, calls the Great Acceleration. You can see it in the number of McDonald's restaurants and paper production and nitrogen use and whatever you like. There's an inflection point here after the end of the Second World War. We started doing a lot more of everything after the end of the Second World War. This is nitrogen use, and you can see that about 2/3 of what nitrogen is being used in North America, Eastern Europe, or Western Europe. So us, essentially. What happens to that nitrogen? This is a very sobering picture, but it also is a very hope-inspiring picture as well at the same time. So here's 100 kilograms of nitrogen fertilizer that some farmer buys. Some of it falls off the truck before it gets out to the field. That's this 6% here. This is what the farmer actually goes and puts on the field to fertilize the crops. And look what happens now. 47% of that disappears somewhere. It goes away. What's left in the crop is 47% of that original 100 kilograms that he bought. But then we don't harvest the whole crop. There's a lot that's left in the field. And so what we actually harvest is 31% of that nitrogen that we originally used. Now the picture diverges a little bit here if you're a vegetarian or if you're a carnivore. If you're a carnivore, let's go down here, then about 7% of that original nitrogen is in the product that you buy. And because we don't eat everything that we buy, I mean, you buy a big slab of meat, you don't eat the bones, most of us anyway, only 4% of that original 100 kilograms of nitrogen ends up in the meat that you eat. If we look at a vegetarian and you eat the grain instead, you're up to about 14% of that nitrogen that was originally applied. So there's a huge loss. There's a huge loss in this chain. And we'll come back to that in terms of solutions. What happens to that nitrogen, that 47% that doesn't get into the plant material? A lot of it ends up here in coastal areas. Okay, it washes off the fields, it runs down into the rivers, it ends up in the coastal areas. And what this is a plot of essentially where we've looked for what's called hypoxic areas, areas of coast to coasts where the bottom water is lacking oxygen. And that's because nitrogen's a nutrient, algae love it, algae will bloom in coastal areas, then they die, they settle down towards the ocean bottom, and they start to decay, and that uses up the oxygen at the ocean bottom. So this is a bit like looking under the street lamp for your keys. This is where we've looked and found hypoxic areas. It's not that there are no hypoxic areas here on the west coast of Africa. We just haven't looked at this point. This is a close-up of algal blooms caused by river runoff of nutrients, fertilizers, from the central part of the United States here. This is the state of Louisiana. Hurricane Katrina went right through there, basically, but you can see that there's a lot of algal blooms close to the coast, which negatively impact fisheries, and particularly shellfish in the area. Okay, so this is the picture for 9 billion people. The picture's changed a little bit. There's more of us over here. The Space Needle has gotten a bit bigger. But here we can see that if we look at the top here, I've drawn some just cartoons of what you might imagine production being. So here's the population or the food that we want to produce with time, and that's growing sort of exponentially. If we look at aquatic protein, so for some time we might be able to ramp up aquatic protein, but we've already seen that we don't have a lot of wiggle room in producing wild fish catch. So if we want to produce more fish, it will be through farmed fish. And you're going to throw something at me soon. Is that, no? Okay, I'm safe. Wonderful. 5 minutes. All right, I'm almost done here. But because we would see more and more algal blooms in coastal areas, because we're using more and more nitrogen to produce terrestrial food, then that would negatively impact our ability to farm fish, because we're farming fish in coastal areas. So at some point, you can envision a maximum in the amount of farmed fish that we produce. And if we continue using the same technology, then that would actually decrease, requiring us to produce even more food from the terrestrial domain. So how do we make this work? Well, the first is we can't use, the conclusion that we have, we can't use that same miraculous, if you will, green revolution technology to go from feeding 7 billion people to 9 billion people. We've got to be smarter than that this time around. We have to come to a different solution. The second thing is, as you saw, there's an extraordinarily large loss of nitrogen in the way we use it at the moment. There's a lot to be done to make that more efficient. There's a whole lot that we can do to make irrigation water more efficient. So there's huge efficiencies to be had in terms of our agricultural production potential. We need a lot of research and development in that area to figure out what those might be and to make them work. We also need to promote what I call here less resource-intensive diets. I don't have the figure with me. It's on my computer, but I don't have it in my head. The amount of CO2 that you would save by only Americans, people living in the U.S., switching from red meat to poultry 2 days a week. It's a tremendous amount of reduced CO2 emissions. Think of if we ate a little bit farther down the food chain a little bit more often, then we could also engender those kinds of savings in the system. We really need to think about optimizing food systems. Oftentimes when we think of food, we think of the production part of the food system. We think of farms, we think of wild fish. It's an entire system. It's the cultural aspects of what I choose to eat. Up in Stockholm, we like potatoes. In Bangkok, people like rice. We choose to eat things. That's a part of our cultural identity. That's part of the system itself. The production part obviously is very important, but it's also how we market the food, how we transport the food, how we store the food, where it goes to waste. So it's an entire system that can be better managed than it is today. And finally, we really do need to rethink our agricultural subsidies and also our marine policy subsidies. In many cases, they're moving us in very much a wrong direction. And I had the privilege of giving a short briefing along these lines to the UN panel on global sustainability about a year ago. And everybody in the room was sort of going, oh yeah, we understand that, till I got to this particular recommendation. And everybody had to check their BlackBerry at that point, because nobody wants to hear about subsidies. They're extraordinarily difficult. They're political hot potatoes. It's tough. But yes, we do have to come to that, to fix that particular part of the system as well. So finally, where have we been? We've looked at living in the Anthropocene. We've looked at transformations for sustainability. We've zoomed in on one of those transformations. And a lot of times I get the question, when you talk about things like this, well, damn, that sounds like we're just toast. Are you an optimist or a pessimist? I've got to be an optimist, and this picture makes me optimistic. That's Frank Noone, the guy next to that's my grandfather, Frank. Okay, everybody, Frank. This was taken, the picture was taken 103 years ago now in Alaska. Frank and company were out looking for gold. Now, I'm here, he didn't find any. But the main point of this particular picture is Frank's transportation. It was horses, okay? So in 2 generations, between my grandfather Frank and myself, we've already transformed the transportation sector. In that same time, we have already transformed our agricultural sector, and we've already transformed the energy sector. Those transformations have occurred in 2 generations' time. We need to make them happen again. And we've got not more than that amount of time to do it, essentially. And finally, the next to the last slide, this one I like a lot because it gives a sense of place. Of course, that's not our planet. It's Saturn. This image comes from the Cassini spacecraft, taken in 2006, but I don't know if you can you see that little dot? Not the red one, but there's a little tiny dot that you can see through the rings of Saturn. That's us. That's our planet. This is the image so far that's been taken of our planet that's been taken farthest away from us. And it really does serve to illustrate that we need to figure this out. We need to make this one work because it's the only planet we've got, and there is no interstellar planetary insurance company that will bail us out. We are, in fact, small enough to fail. So let's not. And with that, that is my last slide. Thank you very much. It's a pleasure and an honor to be here, and hopefully this has started some thoughts. Thanks very much.
I told you that it was good news that we had Kevin Noone here. And I would perhaps allow myself to ask you the first question. If we solve the problems of, in a sustainable way, feeding 9 billion people, won't we be 13 billion people then in a little while? And if we also solve that problem, we'll be soon 20 billion people. So it is there is no solution, or is it one of these games where the grand prize is that you're allowed to play one more time? Please.
Of course, population really is a central issue to all of this, is because it's, the reason why we're pushing some of these boundaries is it's a combination of how many of us there are, but it's also a combination of our collective resource use. So it's that combination that we need to keep in mind when we look at this picture. So if we managed indeed to be able to do all of this stuff that we need to do, then there is not necessarily a cap. But I think if we come back in terms of population, but then let's come back to this. It's hugely important. If every one of us on the planet, if every one of us had the same possibilities to make their dreams come true, if every one of us had the same access to resources, if every one of us was cherished when we arrived on the planet, that's the condition that we want to maximize. That's the condition we want to not only maximize, we want to achieve. We haven't achieved that one yet. Mm-hmm. So I think that kind of condition, it's a little bit seductive to look at boundaries and say, let's manage within this sphere of influence. I think there are other things that we need to probably ask ourselves, what planet, what kind of world do we want, really? And that will say what kind of collective resource impact we can have, and maybe give us an idea of how many of us we want to shoot for, if that's something we want to manage. That's a tough, thanks for asking a real simple question
yes.
first.
Somebody else? Yes, please.
My name is Martin Vigild, and I'm here from DTU. I have a comment and 2 questions. First, the comment which is inspired by your last slide is that a piece of information for everybody, that in the university system and the education system here at DTU, we pick up on this challenge. We have something called Grand Dust. And Grand Dust, Green Challenge, that's a student conference with the focus of sustainability that is going to run every second year and is actually taking place in a few weeks from now. And also, especially with address to your last slide, we also are going to introduce something called Blue Dot projects. And the Blue Dot is, as you introduced it, very far behind Saturn, our spaceship. So these are things that we're trying to do in the educational system, because this calls for a radical change of mindset. Now, my two questions is, how do you pick up the challenge of the incompatibility between the timescales of the problem here and the timescales of human decision, human understanding, and our political system? Because we have magnitudes of difference in the timescales here, and it may be different to take a decision that's going to help your great-great-great-grandchildren. So I'd like you to comment on that. And now there's more sound all of a sudden. I hope you heard everything I said until now, otherwise I will not repeat. My second question is, how do you pick up the challenge on communicating and arguing, discussing with people who either don't understand what you're saying or don't believe what you're saying? Thank you very much.
Right, thanks. Maybe I'll start with the last question first. The ones that don't understand are the ones that you want to keep talking to. And that's fun. That's what we should be doing. That's what we have to be doing. And that's a dialogue and a trust-building exercise, if you will, that needs to take place. And that's enthusiastic. I think all of us involved are enthusiastic about that. The folks that ideologically or for one reason or another will not believe you, I kind of view that myself at this point as a waste of time, trying to convince somebody who will not be convinced of something. And so there's a lot of better time to be spent on actually talking to people who are willing to entertain a new idea, willing to think a little bit for themselves, willing to make up their own minds, willing to be challenged. And you don't have to, at least this is my own personal sort of conclusion after having tried to convince people who will not be convinced, that it's a waste. There's better things to be doing with your time. So that's the answer to the second question. The first one about making things happen. The last year or so, I've had the privilege of working with a small company called Shell, putting this planetary boundaries concept into their strategic development. And with them and with some of their partners, I've actually become enthused and more optimistic. Having in previous positions worked with different parts of the UN system and the political system internationally and seeing nothing happening there of any great import, at least in the environmental area and climate area, I was enthused with the potential that the private sector offers to actually make a decision and make a change. And if you look at major companies like Unilever saying, okay, we will be reducing our environmental input, and here's, we'll put into place things to do that, and then making it happen on a relatively short time frame. That was kind of interesting. And so I'm cautiously, if you will, optimistic that some combination of the private sector actually saying, we're not going to wait for political leadership anymore, we'll actually do something, and the political sphere saying, gosh, okay, maybe we want to be part of this picture as well, rather than watching it go by. That sort of carrot and stick might get us someplace. I'm optimistic there.
I saw somebody over here. Yes, please.
My name is Uffe Bundgaard Jørgensen. I'm normally very optimistic. 3 years ago, I participated as energy regulator in the World Energy Regulator Conference in Athens. And we were accused by Gazprom of all the efforts which we had made on energy conservation because they could not get rid of all their Russian gas. 2 weeks ago, I participated in the same type of World Energy Regulator Conference with participants from all over the world. It lasted 3 days, and the only problem which was seriously discussed was how do we exploit in a better way the shale gas? There was no discussion at all among energy regulators from all over the world about climate change or anything like that. And it's a dramatic change in the same group of people from 3 years ago. So my point is the wheel turning in the political environment against the concerns about climate change right now? And will that last for so long time that we are beyond the tipping point? Thank you very much.
I don't know if you want to re-comment or we should go to a question.
Very, very briefly, there are so many currents, and at the moment it seems like the currents are either flowing in different directions or even colliding with each other. It's the landscape is complicated. Again, we need to we're the first generation really that knows about us having this planetary impact, that's fully aware of that. And I think there's probably still that awareness hasn't gotten to where it needs to get yet. We don't have a lot of time to make that happen. And your point is that it's not happening everywhere. That's entirely true. There's more work to be done.
I saw somebody here. Yes, please.
Jens Hansen from Aalborg University. I think you picked an example to demonstrate that we are not really making a sustainable development. You picked nitrogen. I wonder that, because you had many other examples of where we are maybe overdoing our task and maybe occupying too much of the resources, consuming too many of the resources. Why did you pick nitrogen? Was it so easy, so that's a good reason to pick it and demonstrate? Or why didn't you pick an energy issue or something like that?
Right.
There may be a rationale for having picked nitrogen. Is there?
Well, I guess one of the reasons, the reasons I chose that in particular was we all care about food, and nitrogen is a central part of the food story. Another reason I chose nitrogen was it's no fun just painting a whole bunch of problems if you can't think about solutions to some of those issues. And for nitrogen, that one picture where you can see clearly where nitrogen disappears along that chain of systems allows you to at least start thinking about potential solutions. And I think in terms of the nitrogen in particular, it's a nice example of one of those planetary boundaries where we do have a chance of really reducing, or at least moving back towards that boundary by being a lot more effective and a lot smarter with how we use nitrogen and how we produce food. Yes, oh, very much so, yes. Quite clearly.
I think this answer is a very nice place to stop this discussion, because you mentioned what's very interesting for ATV, that just pointing out a question where we have no idea of a solution, not even perhaps a clue of how we would address finding a solution, is not very interesting. That's essentially what you said. Well, that's what technology is about. So I think from that perspective, we'll thank you very, very much. Thank you.